Here's a good place to start. All right, watch what happens when I turn on watch what happens when water drips from a faucet. Ready? Let me make sure I'm sharing what I think I'm sharing. I am. Set, go. There. So you're looking at waves. You're looking at, in this case, water waves. And you can see what waves do. Waves carry energy from one point to another. So that's probably the crudest or the most simple definition or description of a wave. What is a wave? Well, a wave is something that carries energy from one point to another. So in this case, the wave driver, the thing that's driving the creation of waves, the wave driver is this dripping water. And every time a water falls into the pond, it creates a wave pattern, and it's creating it periodically. So if I actually looked at, let me just take a meter. Let me take a water level meter and put a probe right here. Get this comes with a cello player too, apparently. So let me decrease the amplitude. That sound gets a little bit irritating, but the sound is synchronized with the frequency. So, I mean, what are you looking at? You're looking at a sine wave, and anytime you have a sine wave, that's the telltale sign of simple harmonic motion. So simple harmonic motion results from a restorative force, and the graph of everything in simple harmonic motion is a sine wave. So, I mean, the good news is chapter 16 is looking a lot like chapter 15. It really does. So chapter 15 is very heavy. That's why we spent so much time on it, because it was new and different and heavy. Chapter 16 challenged you to. So check this out. What if I turn down the amplitude? So let's not change anything except for the amplitude. So there's low amplitude. Here's even lower amplitude. Good. So the cello player's quiet. Now, what happens if I crank up the frequency? So right now we're just focusing on amplitude and frequency. Here's me cranking up the frequency. So the dot frequency is cranked up. So you can see higher frequency means shorter period. Shorter period means there's less time required to go from crest to crest or from trough to trough. There's less time required to complete one cycle. All right, so amplitude, frequency. The other thing I should talk about here. Can I turn off this? All right, check out the wave itself. So this wave, this is a train of waves. This is technically these are alternating zones of pressure, or in this case, water level. So again, I put my probe back. You're looking at an alternating series of high water level, low water level. What if I go to sound right here? Check out what happens when I turn on my wave driver. In this case, the wave driver means the object that's creating the waves. You use this last Thursday. You use the wave driver for that resonance experiment. So what if I turn on the speaker? Right now, it looks exactly like the water waves. The only difference here, well, one of the differences is the medium. In this case, the medium is gas. It could be air. It could be the air we breathe. It could be, nitrogen. It could be the surface of Mars, a really thin carbon dioxide atmosphere. But really, it's everything else is kind of the same, except our ears have evolved to hear these pulsations. Now, we don't have alternating water levels. We have alternating regions of high pressure and low pressure. So if I put my probe back, right now you're thinking this looks just like a water wave, but again, the difference is instead of alternating zones of high level water and low level water, it's alternating zones of high pressure and low pressure. And then to our ear, this is what it sounds like. Ready, set, go. And then if I lower the frequency, so this is how our ears are sensitized to pressure differences in this realm, high frequency, low amplitude. All right, so you can see the similarities. And then the last thing that looks similar, again, light waves. So here's basically a source of green light. You turn, or a green flashlight. Just think of this as a green flashlight. A lot is the same. A lot's the same. But the one thing that's different between a light wave versus a sound wave, or between a light wave versus a water wave, is light doesn't need a medium to travel through. A sound wave needs a liquid or solid. And a water wave obviously needs water or, again, liquid. Light is unique. Electromagnetic radiation is unique. It doesn't need a physical substance, a physical medium to travel through. Here's medium frequency. What happens if I crank up the frequency? Ready? There. You go to blue light. And if I crank up the frequency anymore, I go from blue to violet to ultraviolet. So that's the highest energy visible light. If I crank down here, low energy light is red. So infrared light, which we perceive as heat, is infrared light, low frequency, low energy, long period, long period, long wavelength. Right. Okay. So anyway, those are the three kinds of waves in basic form. There's a water wave, a sound wave, and a light wave. And this is just one kind of wave. Let me just check on the old. Let's see if anything's come to life in Wiley Plus. All right, so we're gonna buy some time. I just go over some very bare bones basics. Oh, I'm actually making progress here. All right, so here I'm gonna create our first quiz. Chapter 16, quiz 1. Let's see, maybe things have woken up. Chapter 16, quiz 1 is homework problem 10. So give me a moment to create this, and hopefully you're logging in at some point. It still seems to be quite slow. All right, so I'm going to let that cook in the background. Oop. Yeah, I think maybe it's timed me out, actually. I'll wait on it while I'm waiting. Okay, while I am waiting. All right, there's two types of waves that we're going to limit ourselves
in a
to.
longitudinal wave, the disturbance that
Let me just share this. Okay. So still staying in lecture mode here. All right, there's two types of waves. This is a longitudinal wave, and it's a sound wave, for example. A sound wave is a longitudinal wave. Ready, set, go. So it's like a slinky. So you take a slinky and you do that to the slinky, and this is called a longitudinal wave because the energy is flowing. I should say the slinky is oscillating in the direction of the wave propagation. So there's a few things here. Check out what I'm going to do with my cursor. My cursor, I'm going to follow the wave velocity with my cursor. So ready, 3, 2, 1, go. All right, so check out the velocity. There's my cursor. Notice how that disturbance is traveling at a certain velocity from left to right. So what happens if I do this to the slinky? Instead of pulsing it back and forth, I swish it up and down like that, up and down. And in this case, this is a transverse wave. So those are the key differences. Again, longitudinal wave is the medium. In this case, the slinky is vibrating back and forth in the same direction as the wave velocity. In the case of longitudinal, or I should say a transverse wave, the medium is bouncing up and down perpendicular to the wave direction. So here comes a transverse wave. And this is what I'm saying. The medium is bouncing up and down vertically while the wave velocity is still horizontal. That's a transverse wave. Light waves are transverse waves. Sound waves are longitudinal waves. Speaking of a longitudinal wave, let's take a look at this longitudinal wave particles. This is good.
Does the type of wave like affect anything, like the velocity or anything, if it's transverse or longitudinal? Like, are the light waves faster because of the, I don't know.
No, technically, at this point, we can say there's no difference in between a transverse wave and a longitudinal wave, except for how the media vibrates. Here, this is an outstanding visual. Let me make sure I'm sharing things the right way. Okay, so here we have air. So just think of this as air, a gas. So think of this as like a flute or a piccolo or a clarinet or a saxophone or an organ tube or anything. Think of this as the air in our room at Schoolcraft in room F460. This is a longitudinal wave. And what you see here, we have these three red markers. You see the left marker and the right marker and the middle marker. So just think of these markers as just an individual molecule of air. So let's just examine what happens to the air molecule as the wave propagates from left to right. So again, I'm going to follow the wave along with my cursor. So ready, set, go. So my cursor is just showing the wave velocity. It's going from left to right. You can see that this longitudinal wave, which is occurring in a gas, is producing lower density zones and high density zones. The high density zones are known as condensations. The low density zones are known as rarefactions. So again, we have a left dot, a right dot, and then a dot in the middle. Check out down here below this lower. It's the same exact thing, but I'm tracking. They are tracking. Dan Russell. Dan Russell is tracking what's going on with an individual particle versus what's going on with the wave. So check it out. The wave is going from left to right. We call that the wave propagation velocity. It's propagating from left to right, whereas the media is bouncing back and forth. Now, and here's what really ties a lot of this together. This red dot is bouncing back and forth according to simple harmonic motion. So that's why there is a really strong blend between chapter 15 and chapter 16. Because simple harmonic motion is still part of our toolbox here. All right, and I'm just bouncing back to, all right, still no movement on Wiley Plus, but that's okay. Even if we just have to take notes. All right, and then do the quiz as soon as it becomes available. That's a longitudinal wave. Longitudinal wave, the amplitude refers to the strength of the region of compression or the weakness of the region of the amplitude refers to the strength of the high density zone or the weakness of the low density zone. So even in this more complicated view, you're looking at wave velocity, you're looking at frequency, period, and amplitude. That's a longitudinal wave. Here's a transverse wave. So our friend Dan here doesn't give us the markers, but if we could look at the same red markers, you would see they're still bouncing up and down, but the red markers they're bouncing up and down. They're not bouncing back and forth. In this top diagram, they're bouncing back and forth according to simple harmonic motion. And this back and forth motion is parallel or anti-parallel to the wave velocity direction. Whereas in a transverse wave, if I could isolate a single red dot, it's bouncing up and down perpendicular to the direction of the wave velocity. So at this level, right now, that's the only difference. These waves are identical in every way in terms of amplitude, frequency, period, wavelength, whatever wave velocity. It's just the particles are moving differently with respect to the direction of propagation. If you're wondering what is a water wave, it's kind of both. It's a combination of longitudinal and transverse wave motion. So the interesting thing is water never really moves. So in Lake Michigan or the Atlantic Ocean, water doesn't really move from where it's located. It just sort of sloshes around. It sloshes around. It just basically does this constant circular motion, which is a combination of transverse and longitudinal motion. So water never really leaves home. It just runs around in a circle around its equilibrium position. And then as long as we're here, these are Rayleigh surface waves, which are something or else. I was looking for seismic waves. All right, but anyway, so it's nice to see what water waves are, but we are really going to focus very kind of exclusively on longitudinal waves and transverse waves. So, all right, I'm just going to go see if there's any signs of life with Wiley plus. There aren't. So, but anyway, let's do our first problem. So we're going to do our first problem, which means you guys, you're going to have to take notes. And when these quizzes become available, then you'll be able to finish the quiz really easy. You'll just have a different set of numbers. All right, so here we go. Here's our first quiz. All right, so you have a string. So this is yet another great visual that I can throw at you. Yeah, I just got a message saying the website is under heavy load. So, all right. So we have brought Wiley Plus to its knees. Maybe we should charge more tuition. Maybe that will help. FET waves. Actually, this might be an interesting change of pace. So, all right. So here's waves on a string as soon as it comes up. Okay. So here you have a string, like a guitar string or a piano string or a cello string or string as in string theory. These could be quantum mechanical probability waves. There are a ton of really exotic and really practical phenomena that can be modeled as a wave traveling down a string. So if I do this, let's see, what can I can do? No damping and moderate tension. And what happens if I just...
You're not showing the string.
Okay. So what happens if I start this up, oscillate there. So here's a wave traveling down a string. Okay, so a few things here. Let me restart this again. Restart. Let's lower the amplitude. So no damping. Let's look at what happens with low tension. Low tension. So low tension means not a very tightly pulled string. Low tension, no damping, oscillate, and let's reduce the amplitude. So you're looking at wave velocity. You can actually see wave velocity here. Let me restart it. Ready, go. There. You see this disturbance, this wave disturbance traveling down the string. It takes a certain amount of time. I'm going to hit reset again. Look at that. Ready? Just count it off. So it's moving with some finite velocity along this string. So what if I pause things, restart, everything's the same, but now high tension. Ready, set, go. Go. Ready, set, go. There. So this wave velocity is much greater. Waves travel much faster along a tightly pulled string versus a tight string versus a loose string. But once again, you're looking at, look at these green dots. These green dots represent a particular point on the string. Let me just modify the frequency for a bit and maybe just pause it right here. So this green dot, so for the sake of conversation, let's look at this green dot. All right, in fact, this is a better view of what I have. Okay. Let's go to the notes. I have this here, but that's not bad. This might be better. All right. So let's get into, and you know what you can do when you work on these quizzes. Let's assume Wiley Plus isn't coming back. Let's all use my numbers, and then when you do your quizzes, you just use your numbers, and it won't cost you a ton more time. All right. So this is the wave equation. This is right here. This is what we're going to sort of consider home base right here. This kind of says it all as far as wave basics are concerned. So in chapter 15, just to go back, chapter 15 says, hey, what happens if something is being acted on by a restorative force that's linearly related to displacement? Linearly related means that it's x to a power of 1. Restorative means that negative sign. So chapter 15 was basically hatched from the situation where a restorative force is acting on an object. And if that sounds like really specialized or niche, it's not. There's a ton of things in nature and in practical applications like automotive suspension and door closures and a whole bunch of electrical engineering phenomena that behave according to this type of force. And basically that gave birth to the displacement function. Xt equals xm cosine of omega t plus phi. So chapter 15 was us basically dealing with the position function, the velocity function, the acceleration, and then what else? Well, whatever else we studied force. So as sort of business as usual, the one wrinkle that made chapter 15 unique all by itself was this. We worked our magic on a restorative force, and we said, well, if we use math and physics, we get a position, velocity, acceleration, force, and we talked about damping. What happens if we don't ignore friction? So in the good old days before chapter 15, we talked about kinetic friction and static friction, and in chapter 15, we're talking about this term known as damping and decaying exponential. So, and chapter 15 again is in one sense, it's pretty challenging. It's pretty heavy. In another sense, it's just sort of, hey, let's just do what we've been doing all along, but this is our starting point. In chapter 16, we have something that looks similar. You guys know what a lot of these terms mean. So let's talk about the terms that you know already. You know that T stands for time. You know that phase shift is the amount of head start you get or the amount of back start. So let me just, because that's new as of chapter 15. Let me just go back. And I have learned from experience that phase shift can be a vexing concept, at least for a while. So this is what I'm talking about. Here's y equals sine x. Okay, here's another function. Y equals sine of x plus pi over 18. There you go. There you go. There's a phase shifted sine wave. The red function, red is the unshifted sine wave. The blue function is a phase shifted sine wave. And notice, and this is going to become true in chapter 16, notice that that plus sign actually pulls this sine function back behind the starting line. So this particular sine function is starting behind the starting line. What happens if I change the plus to a minus? Check it out. There. Now my sine wave has a little bit of a head start. So that's true in chapter 15. It's true in chapter 16 as well. But again, the difference between this blue wave and this red wave is a phase shift. So we saw that in chapter 15. Now we're seeing it in chapter 16. Okay. So you know about time, you know about phase shift. You're familiar with the sine function, sine, cosine, tangent, secant, cotangent, etc. But we like sines and cosines because a sine function bounces. A cosine function also bounces. And we like functions that bounce because springs and suspensions and a whole bunch of quantum mechanical types of elements and door closures and stuff, electrical engineering, oscillating circuits, they tend to bounce. So that's why sines and cosines are a big part of this because they bounce. What else do you know about? You know about this. You know about amplitude. Amplitude is here. Let me just do a little bit of a snip. If I go back into Desmos and take a screen snip. Wait for it. Screen snip, waiting for my screen snip. All right, screen snip isn't working. Let me get another picture. Okay, so I'm going to take a little sample here. Okay, this will be good. Here's the notebook. Let me just go to a scratch page. All right, so here's Desmos. Here's Y subscript M. Y subscript M is this dimension right here. Nope, not that, like this. This dimension right here. This is Y sub M. Y sub M has a special name. It's amplitude, but here's I think maybe the most compelling new wrinkle in chapter 16. We have to worry about space and time. So here's the wave function. Y, which is a function of space and time, X refers to space, T refers to time, equals some amplitude times sine of kx minus omega t. Okay, so this is what's on the other page. Y sub m is referring to this amplitude. So naming is important. This is referred to as just, sometimes you just hear it referred to as amplitude. Sometimes you hear it referred to as displacement amplitude. But it's referring to what's going on along that axis, displacement, amplitude. And anything with the word amplitude is referring to a max value. So in chapter 15, we had something known as velocity amplitude, which referred to the peak velocity amplitude. And we also had something known as acceleration amplitude, which is the peak acceleration. So again, that word amplitude refers to the peak value. Okay, so let me go back to what's really making chapter 16 kind of maybe the most profound wrinkle is right here, is the fact that we have to worry about what's going on, not just as a function of space, but as a function of time. So if I look at this wave on a string, say I basically go for a walk and I'm gonna park right here. So I'm going to stand. Say this is a really large string and I'm standing here underneath this green dot. I'm standing underneath this green dot. And when I look at this green dot, I can see that this green dot is bouncing up and down. The green dot is bouncing up and down like this. It's bouncing up and down like that. Okay. So the green dot is bouncing up and down along this y-axis, also known as the amplitude axis. And I'm standing here at some position x. So this would be maybe x equals 0. This would be x equals whatever, 10 meters. So here's the spatial dependency. What this green particle is doing depends on the x value, where you're looking at the green particle. I'm looking at this green particle at position x. The other thing it depends on is what time. Are you looking at this green particle at time equals 1 second or time equals 2 seconds? So we actually have to have two graphs to show waves. To show this wave function, you have to have a graph of amplitude versus position, and then a whole additional graph of amplitude versus time. So I'm making a big deal about this because this is a really common tripping point. It's pretty conceptual, pretty heavy lifting, but hopefully this visual helps because this is the space component and time would just be t equals, again, 4.26 milliseconds. So this is considered a spatial. X is a spatial variable. T is what's known as a temporal. Temporal refers to time. Spatial refers to space or position. So that's why this is a pretty complicated looking function. But at first, like everything, it's difficult at first. So what else do you know about this function? You know what X is. Well, you do now. X is talking about where are we looking at the point on the wave. So again, as mentioned, X right here is just the position in space that we're looking at the wave. We're looking at this particular X location, that particular green dot, and we're going to basically what the position of the green dot along the vertical axis depends on the X variable and the T variable. That's why you see both of those variables part of this wave function. So the other thing that you've seen before is omega. You've seen omega before because birth of a radian, which says theta is defined as arc length over radius, which means I can say S equals R theta. If I divide both sides by time, I can say V equals R omega. If I know that velocity is distance divided by time, distance for the distance here would be the distance of a circle, 2 pi r. That's the distance. The time for that distance is period equals R omega. And that's how we're getting this. This is how we're getting omega equals 2 pi over T, which is the same as 2 pi f. So I just ran through the derivation of omega, again, starting with birth of a radian, and didn't take long. I like to do that every so often just to keep myself rooted in reality, because the worst thing anyone could do is just plug stuff into equations and pray, plug numbers into your equation, hit a calculator, and start saying your prayers. That's not a comfortable place to be. Here's the one new variable we don't know about. This is a brand new introduction to K. This is called angular wave number. Okay. And it's actually a spatial frequency. So terminology is sort of a big part of chapter 16. Omega is a temporal frequency. Omega is something per time. Temporal frequency, which means a time-based frequency. Temporal frequency. And remember what omega is. Omega is 2 pi over T. 2 pi what? Technically speaking, it's 2 pi radians per time. Okay, so omega is a frequency. Anytime you have something per something, that's a frequency. K is wave number. This is a spatial frequency, meaning it depends on space, not a temporal frequency, not a time-based frequency, but a spatial frequency. And we say K is equal to 2 pi radians, again, just like omega, over wavelength. So this is referred to as angular wave number. Angular wave number, whereas omega is angular frequency, angular wave number. And just say it out loud. Just remind yourself what this frequency is saying. K is basically some amount of angle per wavelength. Or you could say it's how many cycles, you have per wave. That's actually saying it the right way, I think. K is angular wave number, and it's the number of cycles per wavelength versus the number of cycles per period. Okay, that's good. So all of that's a lot of background, So I would be going through this, believe it or not, even if stupid old Wiley Plus wasn't down, and I can see it still seems to be down, but let's solve this problem. I just checked. All right. So with all of that background digested, or at least thrown out to you, you know what everything means in this wave equation. I'm going to clear the decks and we're going to solve this problem. Okay, so let's get numbers. You have a string, so here's the problem. The equation of a transverse wave traveling along a very long string is given to us. And we have a picture. So let's pretend this is a very long string and a wave is traveling along this string. And they're actually telling you what the wave function is. So we know generically what a wave function is. They are saying, let me make this easier to read. Okay. They're saying, hey, here's exactly how this wave is behaving. It is doing this. It's saying, for me, it's saying y equals 7.04 sine of 0.085 pi times x plus 8.47 pi times t. So they gave you that. So we know a lot already because we know what a wave function is. This is amplitude. This is y subscript m. This is k because it's kx. So kx means this is k. This is omega. All right. So without even thinking, I can say my wave amplitude is 7.04, and they specified things are expressed in seconds and centimeters. Y sub m is 7.04. K is equal to 0.085 pi. And the units for K, if you look at how K is defined as 2 pi radians per wavelength. So the units would be radian per meter. And technically, I shouldn't write down radians. It's just a placeholder. And actually, I think it's radians per centimeter in this case, because they're giving things to us in seconds and centimeters. Omega is equal to 8.47 pi radians per second. So all of that's just served up to us. A says, what's the amplitude? And the answer is you're done. This is the answer to part A. It's just given to you. And you would just say, well, based on the wave function or based on the wave equation that they give, and then you could just if you just did what I did, that and maybe a comment or two saying, well, according to the given wave equation, 7.04 is indeed the wave amplitude. So we're done with part A. Part B, what's the wavelength? So let's start solving for things. Number one, number two, lambda is the wavelength. Lambda equals wavelength. Wavelength is the distance between, wavelength is the distance it takes a cycle to complete. So in the case of this, here's the wavelength. Well, I kind of cut that off, sort of. Let me get another snip. 1 second while I go back and take a different snip. There. Okay, so let's use this instead. Okay, if this is my y-axis, my amplitude, I'll use those terms interchangeably. Y could be the y-axis or the amplitude axis. This might be the x-axis or position axis. If this is the x-axis, then this is wavelength from this point, from this crest to that crest. That's a wavelength. Or alternatively and equivalently, from this trough to this trough, that's a wavelength. Or equivalently, from some arbitrary point here, wherever, from here to one cycle later, here, that same exact point, one cycle later, these are all wavelength. That's the wavelength. That's a wavelength. That's a wavelength. Okay. If on the other hand, instead of this being an x-axis, if this were a time axis, t for time, y stays the same. But if this were a time axis, I wouldn't call this lambda. I would call it t for period. So that's not wavelength. This would be capital letter T for period. That's a period. That's a period. That's a period. Okay. All right. So step number 3 here. Step number 3, wavelength. That's what we're after. That's the $sign. So I'm going to lean on K, which is angular wave number. Just going to write it out a few times at the beginning. Angular wave number, which is the number of cycles per wavelength. Angular wave number equals number of cycles. Well, 2 pi radian is a complete cycle because it's a circle. Number of cycles per wavelength. So that's the definition of angular wave number, which means I can just do a little rearranging and say lambda, therefore, is 2 pi radians all over K. Or, and again, if you wanted to call the authorities and say, hey, Chris is writing down radians, even though it's not a unit, you would be right. They would come haul me off and put me in physics jail. I'm writing it down just to reinforce what it is. This is amount of cycle. This is number of cycle per, amount of cycle per wavelength. Okay. So what is 2 pi radians divided by K? For me, K is, what is K? K is 0.085 pi radians per centimeter. So from a dimensional point of view, I'm going to end up with centimeters, which I like, because I would expect wavelength to be expressed in some distance unit. So what is 2 pi divided by 0.085 divided by pi? The answer is 23 and some change. 23.529 and some change. That's the answer to part B. We're done with A. We're done with B. Part C. What's the frequency? So this can go pretty fast. I guess I'll get rid of this. No, I'll leave it. So number four says, what's frequency? Number 4 says F. F equals $sign. And birth of a radian said, well, I know omega equals 2 pi F. So then I can just say F equals omega over 2 pi. And my omega is given right in the provided wave equation, 8.47 pi radians per second divided by 2 pi radians equals 8.47 divided by 2, or 4.235. What are the units here? Well, radians cancel, leaving reciprocal seconds. The answer is 4.235 reciprocal seconds which can be written as 4.235 hertz, because a hertz is a reciprocal second, or just 4.235 Hz. Done with C. D says, what's the speed? Right here in your lecture notes. Your lecture notes provided a relatively short and straightforward derivation of wave speed. So, and actually, what is the direction, the frequency, the speed? All right, so let me just get to that. Let me reference that. This is chapter 16 notes. Maybe not. Maybe so. All right, so here's chapter 16. Right here. Okay. Here's a section I'm talking about. These green sheets describe everything. And so there's the complete breakdown in green sheet lecture note form of the wave equation. And then here we just basically cough up some kinematics. And when we do kinematics to figure out velocity, we actually get this expression right here. So if you look at, I mean, I don't want to go through it all right now because it's given to you. These lecture notes are given to you, but this is what I'm looking at. If I remember if I remember that velocity is basically dx dt, and I set things up carefully, I have this expression for velocity. And in my lecture notes, I copy and pasted this into my lecture notes. So generically, you actually have three different expressions for velocity that all mean the same thing. So if you look at this yellow highlighted box here, I have v equals omega over k, or alternatively, v equals f times lambda, or alternatively, lambda over t. Those all are saying the exact same thing. So what do we want to use for part D? D is the wave velocity. So step number 5. D says, what's the speed? How long does it take? So I'm basically saying this. I'm looking at a dot. I'm looking at one of these dots right here, say, for example. And then I'm saying, well, how long that's not going to work out well. The dots themselves are bouncing up and down, as mentioned. So each dot just has this up, down, bouncy motion, up and down like that, up and down. But the wave, the energy is being carried through space and time in that direction. So this is space time. This is a wave traveling through space time. It's going along a position axis and through time. So this is velocity. This is the wave velocity, sometimes referred to as wave speed. It's the propagation. That's a word that's used a lot. Propagation. It's to propagate means to move through or to spread. Propagate means spread, like the COVID virus propagated through North America pretty quickly. So the propagation velocity refers to this velocity as opposed to the transverse velocity. The transverse velocity is talking about, hey, let's look at this. Let's look at this green dot, and then let's ask ourselves, what is the velocity of this green dot from a transverse point of view? So that green dot is bouncing up and down with some transverse velocity, which is u equals dy dt. So we have two kinds of velocity: transverse velocity and propagation velocity, or just regular old velocity. So part D says, what's the propagation velocity of this particular wave? And the answer is whatever you want. I mean, there's omega. Let's just do omega divided by k, since we know those numbers. So this is saying the wave speed is just omega over k, And omega, we already figured that out. Omega was 2 pi f right here. Oh, omega is given. This is omega. I didn't even have to say that much. Here's omega, 8.47 pi. So let's write that down. It's given to you 8.47 pi radians per second. That's the numerator. K is the denominator, and K is right here, kx, 0.0850 pi. So let's write that down. 0.085, and the units would be radians per meter. So from a unit point of view, great news, we do get meters per second. So all you have to do is that division, 8.47 times pi divided by 0.085 times pi. I forgot the pi. Equals 99 some change. So I need, this is 0.085 pi. I forgot the pi. We have the answers to A, B, C, D. The whole purpose of these questions is just to get really familiar with this wave equation, how to apply it, how to interpret it. All right. Part E is saying, what's the direction? So check this out. Let me log into Desmos. Check out this Desmos wave that I have set up right here. Desmos. All right. I think I stored this. All right. So here, check out this graph right here. All right. So this is basically what you're looking at right here that I've highlighted. That's my wave equation with some simplification. Well, that's pretty much my wave equation. Watch what happens when I start playing time, when I turn on time. I start the clock. Ready? 3, 2, 1, go. You can see this wave is flowing in the minus x direction. What happens if I change this from a positive to a negative? Ready, set, go. Now my wave is going in the plus x direction. So I guess here's sort of like the weakest approach, is that you just say to yourself, I say to here's the weakest approach I could take. Okay, negative sign. If that's a negative sign in front of the omega, that means it's moving in the plus x direction. If it's a positive sign in front of the omega, it means it's moving in the negative x direction. So I don't know how cowardly that is. It's not, I mean, I'm not too ashamed to fall back on there, but you do have this sort of like this flip-floppy relationship. A positive in front of the omega means it's moving in the minus x. A negative in front of the omega means it's moving in the positive x. And if you wanted the method to the method to that madness, why is that true? It's well, I guess I'll just go back to Desmos. Right here, let me just stop this. I'll just stop it right. Stop. Let's look at these gray dots. Let's look at, well, I'm turning them black. Look at these dots at the very peak, at the very amplitude. All right, if you look at omega t right here, as time ticks by, this is making, time is actually causing omega t to get really large. So the only way I can keep up with that is if K increases. So Kx is growing. So because as I go from left to right, the product of Kx is increasing. As I go from left to right, the product of omega times t is also increasing because time is flowing by. So if I want to keep this black dot right where it is, I have to have that negative sign. So that negative sign means, hey, you know what? This black dot amplitude is going to remain unchanged because Kx is getting bigger, but it's offset by omega t, which is also getting bigger because both of these, x is getting bigger and t is getting bigger. So that's why you have that negative sign here. And Negative sign means it's flowing to the right. If this were a positive sign, it's the same conversation. If I freeze this, I'm looking at this black dot and this black dot. As things are moving leftward, this X is getting more and more negative. So as things are moving leftward, this is getting increasingly negative, which means you have to offset it by a plus omega t to maintain this amplitude position. Anyway, not sure how clear that is, but that's sort of at the heart. I'm mentioning that because that's going to be applicable in other instances, but let's finish this problem and then take a break, and maybe Wally Plus will come back. Here's our notebook right here. We're done with, all right, so they gave you this. They said this particular wave has this description, and they gave that to us right here. They're saying, that positive sign. This positive sign means, again, negative X direction. Okay, so we're done with A, B, C, D, and E. Last but not least, F and G. What's the maximum transverse speed? So I'm going to get rid of everything because this is getting just a little bit too cluttered. Control C. All right. So transverse speed is referring to the amplitude, the speed along the amplitude axis. So again, I have a particle. Say I have just some arbitrary particle like this. This particle is bouncing up and down along the amplitude axis. So it's just going up to some max point and down to some min point like that. Okay, so this is the amplitude axis. This is the y-axis. A lot of times you'll just refer to it as the amplitude axis. And this could either be the position or the time, one or the other. All right, so transverse velocity is talking about the velocity with which this black dot bounces up and down in this direction, the amplitude direction. So let's do some calculus. Ready? U stands for transverse speed, not wave speed. This is not wave speed. This is transverse speed or transverse velocity. Same thing. And you know what that is? It's just dy. It's dy dt. Because again, we're concerning ourselves with the velocity along this axis right here. So dy dt. So all we have to do is to take the first derivative of the y, of the displacement, of the position function. So we need to take the first derivative of 7.04 times sine of 0.085 pi x, yes, plus 8.47 pi times t. There. How do you take the derivative of that? Well, I know how to take the derivative of sine. The derivative of a sine function is a cosine function. So it's just going to be, it's the same amplitude, 7.04. That's a constant. Sine becomes cosine. The argument remains the same, 0.085 pi x plus 8.47 pi times t. And then power rule means I have to, now it's the derivative with respect to time. So what's my time coefficient? It's right here. Okay. So times 8.47 pi, 8.47 pi. All right, that's it. Let me just do a little rewrite just to organize. So for improved organization, and this was centimeters. I'm just going to say 7.04 centimeters. Yes. Times 8.47 pi. Yes. Cosine of 0.085 pi x plus 8.47 pi t. And then ask yourself, they said, what is the G? What F? What's the maximum transverse speed? So we're looking at and this is a chapter 15 conversation that we're having all over again. What's the maximum valuable? What's the maximum value attainable by cosine? 1. So 1 max value here, max value 1. So whatever this argument is to the cosine function, cosine can at most have a value of 1. So if that equals 1, this is what we're after. We're after what's known as the transverse amplitude speed, or the maximum. Part F says, find the maximum transverse speed. Okay, so what is 7.04 centimeters times 8.47 pi? And the answer would be 7.04 times 8.47 times pi, or 187 and some change. And that should be meters per second, 187.3294 meters per second. The last thing we need to do here, centimeters per second. Okay. Plug and play. So let's just do plug and play. Plug and play the following values. Go ahead, plug X equals 2.35 centimeters and plug in T equals 0.624 seconds into our wave equation. So here goes. It says, where is this particle? So right here, let's just say, let's use this as our example. At X equals 2.35 centimeters, 2.35 centimeters. So this X value right here, this is X equals 2.35 centimeters. So this is the X axis. And at time equals 0.624 seconds. So I guess this is doubling as not only the X axis, but also the time axis. Let's figure out what this value is right here. This is the dollar sign. Okay, this is what we're after. So here goes. Y equals 7.04 centimeters times sine of 0.085 pi times X. Here's the value of X. X has a value of 2.35 centimeters. Got to be careful with units. Plus 8.47 pi times time. And time is 0.624 seconds. So you need to plug that into your calculator. I need to make sure centimeters good with everything here. Yeah, because it's saying, hey, we're living in the realm of centimeters and seconds. You need to have your calculator in radian mode. So go ahead and flip your calculator into radian mode. And let's do number 6. 7.04 times sine 0.0. And I'm not in radian mode, I just discovered. So go from degree mode to radian mode. Okay. -7 and some change. So it turns out I'm actually below the axis. So now I know where my particle is at this particular X position in this particular time. It's actually below the equilibrium point. So it's actually down here. I'll move it. Okay. Too much trouble. my particle is living down here. Okay. So that's a very long problem that gets us, that's pretty good coverage of the wave equation and wave basics. And it's very, this is a major pillar of physics. This pertains to door closures, automotive suspensions, quantum mechanics, everything that kind of vibration control, Bose, noise cancellation headphones, although I happen to have Panasonic. So anything to do with sound or waves or vibrations, this is at the heart of that stuff. So I'm trying to think of what branch of science or engineering never has to worry about waves. And the answer is I can't think of anything. I mean, if you want to, good luck finding a branch of science or engineering where you don't ever have to worry, where you'll never have to worry about this stuff. And let me know. And then what you have to do is say, well, I'm never going to change my mind. I'm going to go into this field and I'm never going to change my mind. So let's see, 211 CU at 221. So between now and 221, hopefully Wiley Plus will come back. If not, then we'll just carry on the way we're doing now and make amends later. So see you at 2:21 p.m. Well, it looked like Wiley Plus was back for a moment. In the last few minutes, it seems to be gone again. I made some progress. I don't know if you were able to log in, but I think we're just going to have to continue on the path we're on, and then I'll just extend these deadlines. I'm not going to cancel these quizzes because that's just not a responsible thing to do. But I also want to announce one other thing, as long as we're talking about policies here. Let's keep the deadline for the chapter 16 homework on Sunday. And I want to do that because I want to keep the chapter 16 homework deadline on Sunday in place, because then I want to use kind of the remaining time as focus on review. So if I look into the course calendar, let me go on record, make sure nobody is not hearing this announcement. I am officially saying that the chapter 16 homework is in fact due Sunday, December 12th. So this will be, and I can fix that typo at the same time. So this is chapter 16 homework deadline with the typo fixed. And I guess that's 10.5. All right. So just same old homework deadline. And that, again, that gives us some back end breathing room instead of dragging on chapter 16 for too long. Okay. All right. So I guess because Wiley Plus still seems to be, yeah, I think it's still out of it. So let's just go on. Let's just go on and do the next problem. Although one more look, one more visitation. Let's see. Chapter 16. Quiz 1 is there. So let me see. Quiz 1 is now available to you. Let's see what quiz 2. Maybe there's these windows of normalcy. So yeah, as of right now, things are bouncing around just fine in Wiley Plus. We'll see how long that lasts, but 1 a.m. to 6 p.m. December 7th. Waiting again. Okay, so I think it's looking okay-ish. I gotta look at one more thing for quiz 2. As I'm doing this, just see, the goal is for you to be logged into Wiley Plus and clicking yourself into chapter 16 quiz 2. And I understand that might not be possible because I think I'm not really doing much here. Well, okay, I guess I'm going to bail out. It was working for a bit. So again, here's the plan. You guys just pay attention, learn, take notes, and then reapply the solution that's working for us right here to your quizzes when Wiley Plus becomes available. We'll figure out what makes sense as far as the deadline. Again, I don't want to cancel these quizzes because that means you'll go way too long without really getting your hands dirty with this stuff. So we're going to move on to the next quiz. Let me clear the deck here. Yep. So here is our second wave problem. And let me just repeat what I'm thinking is going to work for you. You take notes, you follow along, you learn, you get, and then you'll get the right answer when Wiley Plus comes back. But for now, we're just learning. All right, so now we have another wave. That's another wave going along a string. All right, so this is quiz 2. All right, an interesting graph. Check out the graph. This is not a graph of amplitude versus position or amplitude versus time. It's a graph of slope versus position. Interesting. Slope versus position. This is the graph we have. We're going to do graphical analysis to pick off meaningful points. And I guess right now, this is a meaningful, this seems to be a meaningful point right here. And maybe there's some other meaningful, the one other thing I can see is if this is X, this would be wavelength. So that's another key piece of data we can get from the graph. From that crest to this crest, that's wavelength. So there's lambda. So just from this graph, I can tell that lambda is the distance between two adjacent points. And in this case, it's going to equal X subscript S over 2. This whole distance right here is X subscript S. But my wavelength is just going half that distance. So that's meaningful stuff from the graph right away without any delay. The question is, what's the amplitude of the wave? This question is saying Y sub M equals $. Okay, that's what we're after. So let's get to work. Number one, I'm going to start with slope. Slope. The slope that we're looking at is equal to dy dx. I was going to write down, I came within inches of saying, I almost said slope equals dy dt, but I stopped myself because I'm looking at the graph. It's saying a sinusoidal wave travels along a string under tension. The figure shows the slopes along the string at time equals 0. So just based on what the graph is, it's something versus X, and it's the slope along the string at time equals 0. That's why I'm saying dy dx. But I did have to think on that. Is it dy dx or dy dt? Dy dt is transverse velocity, and that's not what we need here. So I need to take the first derivative with respect to X of the given wave function I don't know what that is. So I don't know what well, I guess let me go with the generic wave function. What is the first derivative of the generic wave equation? So what's the derivative of y sub m times sine of kx minus omega t plus phi? I know how to take the derivative of that. The slope, that slope equals the derivative of sine is cosine. So cosine, sine becomes cosine. This constant remains unchanged. It's the same argument, kx minus omega t plus phi. Power rule says what's the constant of not time, but of x right here. So last time I actually took this constant because I was doing dy dt. That's not what I'm doing here now. So I take the k times k. So if I rewrite this one more time, the slope equals y subscript m, the amplitude, times k, the angular wave number, cosine of kx minus omega t plus phi. All right, so now you're looking, this graph is basically a snapshot at time equals 0. So let's talk about some low-hanging fruit. This graph is what's happening at time equals 0. Low-hanging fruit. 0. I'm going to look at this point right here, this point that I circled in red. This point, 0, sorry. This point right here at x equals 0. So once again, I'm looking at this point right at x equals 0. So x equals 0, and the value of the slope at x equals 0 is, for me, 0.3. Right there, that red dot. All right, so more low-hanging fruit. I'm looking at x equals 0. X equals 0. And you know what? The slope at all this is 0.3. 0.3. So here's my simplified expression. I have 0.3, 0.3 equals y sub m times k times cosine, x is 0, so that disappears. T is 0, so that disappears, times phi, the phase shift. And now the question is, what's phi? What is the phase shift? What's phi? And the answer is 0. Phi equals 0. You know why? Because here's my function. I'm looking at y sub m times k times the cosine of whatever that argument is. So if this is my function, and if this is my graph right here, look at my graph. My graph is just a standard cosine function. That's not a shifted cosine function. If you want to see what a shifted cosine function looks like, we would just go into Desmos, and I would say, okay, I want a cosine function. Here's the cosine function. Let me share, make sure I'm sharing. I am. Here's y equals cosine of s. Y equals cosine of x. Okay, that's an unshifted cosine function. Here's a shifted cosine function. Y equals cosine of x minus pi over 10, for example. All right. So blue is a shifted cosine function. Red is an unshifted cosine function. So if it's an unshifted cosine function, means the peak occurs at 0. And that's what we have. That's what we have in our instance here. The peak of this function is occurring at 0. So no shift. This means you are looking at unshifted cosine function. So that means phi equals 0, no shift. All right, so now this is what we have. We have 0.3 equals y sub m k times cosine of 0. Cosine of 0 equals 1. So great success almost. I have my dollar sign. My wave amplitude equals 0.3 all over k. So then, what's k equal? Well, k is, again, k is angular wave number, the amount of cycle per wavelength, angular wave number. That's what k is. So here's what I can say. 0.3 all over 2 pi over lambda. 2 pi over lambda, because k equals 2 pi over lambda. Amount of cycle per wavelength. And the units would be radians per meter. All right, the only problem is what's lambda? So the challenge continues. Lambda equals xs over 2 based on my early graphical observation. So for me, x subscript s is 0.75 meters divided by 2. Okay, so here's the answer. The amplitude of this particular wave based on that graphical information is 0.3 divided by that. My numerator is 2 pi radians all over lambda, which is 0.75 meters divided by 2. That's my wave amplitude. And the units, yet the units do work out as meters. So calculator time. Okay. All right. So that's using some detective work applied to a graph and our knowledge of the wave equation. All right, let me take a look. That's that problem. Didn't take long. Let's see what's new in the mysterious world of Wiley Plus. I don't think anything's new. Okay. All right, quiz 3. Wait, hang on, it came back. Let me just see. You never know, so let's see if I can. So anyway, quiz 1 and quiz 2, I believe, are now available to you, and I'll push back the deadline if I need to. Right now, the deadline is 6 o'clock. Maybe that'll be okay if things wake up. Maybe I need to adjust that. We'll figure it out before we end today. But quiz 1 and quiz 2 are now viewable or accessible to you. And it's still kind of sludgy slow. So I'm just going to go back to the notebook. Back to the notebook and do quiz 3. Here's quiz 3. This looks pretty involved. Quiz 3. There is a case to be made for doing things this way. And I know I'm rationalizing, but rather than worrying about calculating, rather than frantically punching numbers into your own calculator and clicking on Wiley Plus, maybe you're more focused on what I'm doing here. Not again, I don't mean this as an egotistical, like, hey, pay attention to me. I'm saying if you take away all of the panic associated with punching numbers into a calculator and clicking on Wiley Plus, maybe there's some advantage to that. That's my positive spin. All right. So,
Professor,
yep.
if Wiley Plus isn't back in time, I do work after this class, and I was wondering how late you were planning on like leaving the quizzes.
Either sometime today or tomorrow, sometime either late tonight or sometime tomorrow. So whatever works. Like so I mean, if you're telling me you work until later tonight and there's a lot of work ahead of us, then I'll just say, hey, maybe I'll push everything off to tomorrow, but let's have that conversation at the very end, just so everyone can get accommodated. Because
Okay.
Right now, no one's going to be left behind. Nobody's, but again, I don't want to cancel these, and I don't want to make these due in like several days, because that means that's too long. That's going too long without touching physics, but we'll do the right thing. And hang on, I'm having some luck here on quiz 3. This is very exciting. Okay, so save, wait for it. Yeah, I'm kind of assuming everyone has something to do when this class ends. So I'll just change the deadline to whatever it needs to be to satisfy everyone. All right, so quiz 3. Well, I don't know. It seems to be stuck again. It comes in intervals. All right, so I guess I'll get started. Yeah, now I get a timeout. Okay, so I hope this doesn't happen often. Let's do this problem. So by the time we're done with these quizzes, we're going to be really familiar with all of these various properties of waves, which is good. That is a gratifying accomplishment. We have a graph. So as soon as I see a graph, you look at what is this a graph of very specifically. In this case, it's a graph of transverse velocity versus time. The figure shows the transverse velocity u versus time t of a point on a string at x equals 0. So you have a sine wave. So this is what's going on visually before I come back to this. Okay, so you're standing at a certain position at x equals 0, I guess. So you're standing at x equals 0, and you're going to watch this wave basically pass you by, but you don't care about any part of this. The only point that you're looking at is this green dot right here. You're going to look at how that green dot behaves as far as its transverse motion is concerned. So from there, you're looking at that green dot at x equals 0. What is it doing as a function of time as far as its position along that amplitude axis? So I always try to have those conversations, at least internally in my own head, because without that, if I don't have that conversation, then again, I'm just an equation manipulator, which is, for me, I find that enormously uncomfortable because it's Russian roulette. And I've never been good at any kind of gambling. All right, so we're looking at a point on the string at x equals 0. We're ignoring all of the points before that and after that. And things are scaled for us. So I'm instinctively looking at this point, that peak point right there. There's a peak point. That's sort of a natural point that catches your attention right there. And I'm looking at this point right here. Those are nice identifiable points. All right, so if we have this graph, the question is, what is the phase constant? And it's tricky. There's some trickiness involved here. But right now, number one, it's saying, what is phi? So number one, phi is the dollar sign. What is the phase shift? And clearly, this is not, you're not looking at an unshifted, this is not cos theta, and it's not sine theta, it's cosine theta with a phase shift, or equivalently, you could say it's sine theta with a phase shift. But this is a shifted function, because if it was sine, it would look like this. That's what it would look like if it were sine. If it were cosine, it would look like this. Cosine would look like this. And it's not. It's neither of those, so it's shifted. So, all right, let us proceed. Number two, if this is a graph of transverse velocity, which again is referring to the velocity with which this red dot is bouncing up and down along that amplitude axis, it's that velocity. It's not this velocity. No, it's not that velocity. It's this up-down velocity. Okay, that's what we're looking at. All right, number two, let's see. Well, U equals dy dt. So another chance to take the time derivative of the position function. They gave you the position function. They said to use this, and they didn't really need to do that. This is just the standard wave equation. So what is the time derivative of y subscript m sine of kx minus omega t plus phi? We have to take that time derivative. Here goes. We're gonna get good at taking derivatives of sines and cosines. All right, I have cosine of that function, of that argument, kx minus omega t plus phi, and here's y sub m, that remains unchanged. And power rule says, what is the coefficient of my time variable? It's right here. It's minus omega t. So let's take that as well. Right here. Okay. Minus omega. All right, so here's my general expression for transverse wave velocity, which is a function of x and t. It's a space-time function, equals negative y sub m omega cosine of kx minus omega t plus phi. So far, so good. Now I can peel some points. I'm going to do this. I'm going to let's look at this point, number 5. At x equals 0 and at t equals 0, this whole graph is at x equals 0. At x equals 0 and at t equals 0, so this is t equals 0. The whole graph is at x equals 0. At x equals 0, t equals 0, this is what I have. The transverse wave velocity at x equals 0, t equals 0 equals -8. For me, that's -8 meters per second, because it's 2, 4, 6, 8 u sub s. So -8 meters per second. And that also equals negative ym omega cosine of, let's do the low-hanging fruit. This is at x equals 0, this whole graph, x equals 0. We're looking at the specific time point at time equals 0. So this is what we have. That's it. Number 6. All right. So I have well, I guess I don't have anything more. That's all I can say. So this is my dollar sign. I was going to solve for it, but that's my dollar sign. And I know but I don't know this. I don't know either of these. So this is my uh-oh moment. So I'm going to look at this data point right here. Look at this data point. At that data point. So that data point is saying the following. It's saying Umax, the maximum transverse wave velocity is for me 2, 4, 6, 8, 10 equals 10 meters per second. And here's my generic transverse wave velocity function. So 10 meters per second equals this right here. Okay, so 10 meters per second equals y sub m times cosine. Well, let me do this. Y sub m times that negative y sub m times omega times cosine of kx minus omega t plus phi. So here's some detective work now. Because remember, if you want to go into science or engineering, you have to be rational, logical, and at the same time, imagination, to quote SpongeBob. So here's a question. If this entire right side equals 10, I can for sure say that this expression right here, this has to equal -1. Because you can see, if I'm looking at this point right here, this is a max point. That is the maximum point. Cosine can range. So cosine can be as great as 1 or as little as -1. And in this case, it's -1 because I have to have this negative sign right here. This negative sign has to multiply by another negative sign to crank out 10 meters per second. So you know what I can say in step 7? That's my creative part. Now I can say, because I had that creative insight, I can say in step 7, 10 meters per second equals ym omega. So, great news. Because again, this whole thing has to equal -1. It has to be an absolute max or min point. And in this case, it's a min point because I need the negative times a negative to equal a positive because it's positive 10. All right, so number 8. Let's combine number 5. If you look at equation number 5 and number 7, equation number 5 and number 7, now I have the following. -8 meters per second equals -10 meters per second times cosine of phi. That's what happens when I combine steps 5 and 7. So that means number 9 is cosine of phi, my phase shift angle, equals 0.8. And you know what that means? Phi is going to equal plus or minus arc cosine of 0.8. And that equals, calculator says inverse cosine of 0.8 is 0.6435. Make sure you're in radian mode. 0.6435 radians, plus or minus. So we have to find out, is it plus or minus? In fact, we should talk about why is it plus or minus? And this is where we have to remember the unit circle. Here's the unit circle once again. Why do we have a plus or minus situation here? All right, if this is my unit circle, cosine, all right, so this is what I have. My result has to be 0.6435, which means there are two options. I could have, this might be my angle like that, or conversely, this could be my angle like that. Okay. So maybe it's phi equals positive 0.643, or maybe it's phi equals negative 0.6435. In either case, the cosine is going to be 0.8. Because remember what cosine is measuring. Cosine is basically measuring this x point right here, that blue dot. The x coordinate of that blue dot is cosine. So you have two choices. So now we have to use a little bit of detective work to find out. I'm getting a monthly test of the Livonia wireless emergency test. This is only a test. I thought maybe that was Wiley Plus coming back. All right, so this is a test of the Wiley Plus emergency broadcasting system. All right, so which is it plus or minus? Is this phase angle located in quadrant 1 or located in quadrant 4? So let's do some detective work. Here's a bit of detective work. This is a pretty common tactic to use, sort of like slope test. All right, so and in fact, they tell you caution. A calculator does not always give you the proper inverse trig function. So check your answer by substituting it. And anyway, it's saying you got to figure out if it's plus or minus. So I'm going to take a tangent. I'm going to draw a tangent line. So here is a tangent line right here, tangent to this point right there. Let me fix that right there. All right, this blue line is tangent. It's tangent precisely at this point right there. All right. So I'm drawing that tangent line because I know at that point x equals 0 and t equals 0. So that might yield something pretty easy to deal with, because not only does x equal 0, but t equals 0. And let me label this. This here. This is the slope of this tangent line. The slope of this tangent is greater than 0. You can see that the slope of that blue line, that's a positive slope tangent at, and this is at x equals 0 and t equals 0. So you know what I'm going to do? I'm going to use calculus to take, what is the slope? What is the expression for the slope of that blue line, that light blue line? Calculus says the following. Calculus says number 11, slope of that light blue line is equal to du dt. Du dt is the slope of that blue line. So I need to take the time derivative of my transverse velocity function, which is sitting right here in step 3. So here's step 3. Step 3 is minus ym omega cosine of kx minus omega t plus phi. Okay, so let's take the derivative. What's the derivative of cosine? The derivative of cosine is negative sign. So we need to be super careful here. Let's see, du dt, or disaster ensues. So du dt is, okay, careful. My negative y sub m, nothing happens to that. Omega, nothing happens to that. Derivative of cosine is negative sign. So this is going to be negative sine. I'll do it like that. There's negative sine of this angle, kx minus omega t plus phi Power rule says if it's a derivative with respect to time, I need to then multiply by the coefficient of time. So I'm going to multiply by minus omega, another minus omega, minus omega. All right, so I got to sanity check that because things are flip-flopping all over the place. Let's see. I know the derivative of cosine is negative sine. So negative y sub m, don't need to do anything to that. Don't need to do anything to omega. Yeah, here's the negative 1 that goes along with negative sine. Here's the sine of the same arc. I think that's right. I think this is correct. So if I simplify that, number 13, simplifying, number 13 says the slope equals negative times a negative times a negative. So I have 3 negatives. I'm going to take this negative times this negative times this negative, which produces a negative. Negative times a negative times a negative is a negative. So negative y subscript m omega squared sine of kx minus omega t plus phi. Now I can evaluate it. Now that I did all the heavy calculus work, I can eval at x equals 0 and t equals 0. Because again, I'm looking at this point. This is the point I'm looking at right here. I'm looking at t equals 0, and that whole graph is again a snapshot taken at x equals 0. So I have step 14. The slope is going to equal negative y sub m omega squared sine of phi. And then finally, the aha moment. Aha. Since the slope is positive, since du dt must be greater than 0, because look where I drew the slope. Here's my slope. My slope, which is the slope of the tangent line, this is my tangent line right at that red dot. That's a positive slope. That is for sure positive. So doing the slope test means the following. It means, therefore, ergo and therefore, sine of phi must be less than 0. This beast right here, this chunk has to be negative, because this negative times this negative will produce a positive, and it is positive 10. It is greater than 0. So phi is less than 0. So therefore, phi is less than 0, or phi equals negative 0.643. Okay. So we spent more time talking about is it positive or negative than we did actually getting the answer, which is good. That's talk about splitting hairs in a good way. All right. That's that. Time check. 3:05. Let me just take a quick peek at any signs of life. Chapter 16. Let's see, chapter 16. All right, so 1, 2, and 3 are now good to go. Let's do this. 306. See you at 3:15. See you at 3:15 p.m. and we'll hope for the best, but assume the worst. Okay. onward. Next quiz. Wait a minute. Okay. Chapter 16, quiz 4. Looks like a short one. It is a short one. All right. Okay. We have yet another wave on a string. Basically, this chapter is chunked up into wave basics, waves on a string, waves on a string, and then it kind of culminates with standing waves. Standing waves and resonance, and standing waves and resonance is the heart of Thursday's lab. So probably we'll spend a decent amount of time on Thursday doing some more of these quizzes. But these are the 3 fundamental subtopics of this chapter. So we have, and I think most of today is I think, dedicated to wave basics and waves on a string. Okay, so we have another string with a wave with waves traveling through it. Okay, we know the function. So they actually give us, they say, well, for this particular wave, y, which is a function of space and time, equals 23 centimeters times cosine of pi x minus 21 pi t. That's the wave function. So we can say the following. We can right away, just through observation, we can say y sub m. I don't want to use purple. We can say y sub m equals 23 centimeters. We can say that k equals pi. We can say that omega equals 21 pi. Fine. Notice this is a cosine function, whereas here, the standard wave equation uses the sine function. So why is this using cofunction? And the answer, why is this using cosine? And the answer is it doesn't matter, because a sine function is nothing other than a cosine function phase shifted. So I want to stress that into oblivion. So let me just one more time go into Desmos and say, here's a cosine. Well, here's a sine function. Y equals sine of x. And then here's a phase shifted sine function. Y equals sine of x minus pi over 2. Actually, plus pi over 2 there. So both of these are sine functions, but if you notice, this green function looks just like a cosine function. So a cosine function is nothing more than a sine function shifted backwards. Why am I saying backwards? Because that's a positive sign. Phase shifted backward, pi over 2 or 90 degrees, pi over 2 radians, which is 90 degrees. So it doesn't matter. We don't have to get too overly pigeonholed with sines or cosines, because one is just a phase shift of the other. Anyway, that's our wave function. Let's go on and let's see. What's the transverse speed? All right, so what's the transverse speed? So 2 says u, the transverse speed. What is the transverse speed when the string, what is the transverse speed if if the y position, oh, that's interesting. So right now I'll just say u, which is a function of x and t, equals the $sign when y, which is a function of x and t, equals 0.2 meters. I'm just going to go from centimeters to meters. I'm going to convert this right away to meters because I can see that I need to cough up meters per second as my answer. So this is the question. What's my transverse wave velocity when my location? So basically here, I'll draw that. Here's my cosine function. Ready, set, go. There. So it's basically saying, let's just take a particular point right here. Let's look at this point when it has this y value. This y value over here is equal to y sub m. Let me move this over. Okay, y sub m equals 20 centimeters or 0.2 meters. It's saying at this particular moment, that red dot has a transverse velocity, and the transverse velocity is this velocity. It's the amplitude velocity, this up-down velocity. So we're basically saying, what is that transverse velocity at that particular y location? Doesn't matter. Well, let's see. I don't know what doesn't matter, but this is what we have to figure out. Number 3. Okay, so let's do so if y, let's find out y, which is a function of x and t, equals 0.2 equals 0.23 cosine of pi x minus 21 pi times t. So that's something, because I got to find u subscript t. This is my $sign. So from number 3, the only thing I can get out of step 3 is the following. I can say cosine of pi x minus 21 pi t equals 0.2 over 0.23. And the other thing I should add, just this has caught my eye, I can also say phi equals 0. There is no phase shift. This is an unshifted cosine function. Okay, so anyway, back to it. How does that help me? I don't know. But I'll say this. I can't help but notice out of the side of my eye that if this was my answer, well, what is the transverse speed? All right, so basically this is what I coughed up from my position function. I need to find my transverse speed. So time to do that. Okay, so my transverse speed is u is going to equal dy dt. So one more time, I need to take the time derivative of my position function, and specifically the amplitude position function. I need to take the time derivative of 0.23 meters times cosine meters. I'll include that, I guess. Meters times cosine of pi x minus 21 pi times t. So when I take that derivative, the transverse velocity function equals 0.23 meters. The derivative of cosine is the negative sign. So here's negative sine, same argument, pi x minus 21 pi t. Yes, that looks good. Power function times the coefficient of the time variable, which is right here, times negative 21 pi. Negative 21 pi. Okay, let's simplify that. Transverse velocity function equals, I have a negative times a negative. Okay, so I have 0.23 meters times 21 pi times sine of that argument, pi x minus 21 pi t. So there's good news though, because I can't help but notice that I know what this argument is right here. What if I just call this? What if I call this expression right here the argument of cosine in step 4? I'm just going to call that alpha. So alpha is just going to be pi x minus 21 pi t. This is the same alpha here. Okay, so I can say this, number 8. So if I look at number 4, I have the following. I have cosine of alpha equals 0.2 over 0.23. And that means alpha equals inverse cosine of 0.2 over 0.23. And whatever that equals, well, that equals inverse cosine of 0.2 divided by 0.23. That equals 0.516 and some change. And let's store that in calculator memory A. So number 9 I can conclude by saying, here's the answer. The transverse wave velocity, when this red dot is at that particular location, positive 0.2 meters, is going to equal, I guess I'm just plugging this in. Equals 0.23 meters times 21 pi times sine of alpha A, because it's the same argument. Store alpha A. Okay. Let's take the sine of alpha A times 0.23 times 21 pi, 7.49 and some change meters per second. Okay. That's finding the inverse wave velocity or the transverse wave velocity using some creative tactics. 7.493 meters per second. Okay. Chapter 16. Let me take a look at Wiley Plus. Scanning for signs of life. It's working. It seems to be working somewhat, but I don't know. I don't think. I'm guessing that you guys either can't log in, or if you can log in, you're moving at a glacial pace.
Yeah, mine's not loading at all. So
Right. Yeah, and I'm kind of stuck. So just proceeding. Let's just proceed. Let's do 2 more problems. Let's do 2 more problems this way. Next. Okay. and we break into some new territory. We're actually going to talk about wave velocity on a string. So this is new. This was derived. This is sitting here in your green sheets, which I will make available via, I don't know if I mentioned this. I'll make the green sheets available to you as filled out as scans, images of the completed green sheets will be, I'll post those. So you can just, instead of watching a video and transcribing from the video, you'll just page through these images and transcribe from the images that I make available. Make sure you learn as you transcribe. And for sure, you're going to have to lean on rewatching. I said this before, I'll say it again. I'm assuming everyone here rewatches these Tuesday Zoom sessions once or twice or three times. So again, I'm not going to ask for details, but that's kind of standard practice. If you haven't been watching these Tuesday sessions, these recordings, rewatching these recorded Zoom sessions, good news is it's going to help a lot when you start doing it. All right, so here we go. If I look at the green sheets, speaking of green sheets, there is a derivation here that's based on force analysis method. And here it is. So in this section, we're saying, hey, let's look specifically at wave velocity traveling through a string, which again, a lot of things, it turns out a lot of things in nature and in modern society can be modeled as a wave going through a string. A lot. Snare drums, for example, noise cancellation. It's all kind of, this is like the basis for all of that higher end stuff. But if we take a little string segment right here, a little teeny tiny string segment, and we say, well, let's study what's going on with this little teeny tiny string segment. I'm going to do force analysis. Here's my free body diagram. It's all labeled. Here's my expression for acceleration. Here's doing some trig. So this is garden variety, straight ahead, force analysis applied to this little teeny tiny sample representative string segment. Okay, so we do force analysis and we actually get two new results. We're going to talk about something known as string linear mass density. And this is the result. We do the force analysis on our sample and we get this result for velocity. So you know what that means. We now have a generic expression for velocity. So based on the prior conversation earlier today, here's wave velocity for a string. Wait, in general, wave velocity, forget, it doesn't have to be a string, but wave velocity is omega over k, which turns out to be exactly equivalent to frequency times wavelength, which is then, of course, the same as wavelength over time. Now, specifically for a string, because of the force analysis that we just did on a string, we also have another velocity expression for a string, square root of t over mu. So all of these are equivalent. These are all related. These are all basically saying, hey, here's the velocity of a wave going through, going across a medium, through a medium. In this case, the medium is a string. And this expression right here is the very specific velocity for string velocity, like a rope or a cable or a wire, whatever. All right, so, and I have that right here. This is string tension. And you'll be using this equation on Thursday. This is mass density. So this is mu equals the mass of the string per the length of the string. So then if you wonder, how are you going to get a string to be under tension? This is kind of what you're going to be doing on Thursday. Let's say, for the sake of conversation, this is a length of string. All right, on this end right here, on the left end, maybe you'll knot this. You'll you will tie this. You'll anchor that somehow. You'll anchor that left end. And then on this right end, maybe you'll hang this over a pulley. So here's a pulley. And then you'll just have a hanging mass. Like that, a hanging mass. So this is one way to create string tension. So basically, the string we're looking at is bounded between these 2 points, that point and this point. Okay, so that's our length of string right there. And that's how you can have it be in tension. All right, so what you're going to do is there's a pulse. So we're going to send a pulse along the string. Let me look at this one. So here's what's going to happen. If I restart this. All right, so watch what happens when I do a pulse. Here's a pulse. Pulse, ready, 3, 2, 1, go. Ready, go. All right, that's a pulse. Let me make that a little more dramatic. A big pulse. Okay, a very abrupt pulse. So here goes. Ready, 3, 2, 1, pulse there. And then you get this reflection. So if there's no damping, it's going to go back and forth forever. It's going to reflect. So this is like echoes, and this is how standing waves are created, all stuff that we're going to look at on Thursday. But I'm going to create a pulse from the left side. So this pulse is going to get created and go from left to right. All right. Then in the case of our specific problem, you're going to create a pulse on the right side and send it leftward. So let's use this orange dot, or this red dot is the pulse leaving from the left side. So I have this pulse here. Well, I'll draw it like this. Make this easier to look at. So I have a red pulse here at this end. And then I have a blue pulse at that end. So this red pulse is generated and takes off flying down the string in this direction with some velocity V. This blue pulse is generated on the right end and comes flying in this direction towards the red pulse. And at some point they meet. So they meet when the red pulse arrives to, say, there, just for example, and this blue pulse meets it. So those pulses meet. And the question is, where do they meet? What is this X location? That's our $. X final equals $. So let's do kinematics. This is the kinematics situation. All right, ready. And then we're going to call this, we'll call this pulse 1. Red will just refer to pulse 1 as red. And that blue dot we can refer to as pulse 2. Blue dot is pulse 2. Okay, so let's do kinematics. X initial, X final, VX initial, VX final, A sub X, and T. And then we have to do it for pulse 1. And then we have to do it for pulse 2. All right. So for pulse 1, here's X initial for pulse 1. X initial equals 0. So here's pulse 1. Ready? X initial is 0. X final is $. Oh, hang on 1 second. 1 second, you guys. Okay, sorry about that. That's the furnace repairman on his way to fix our furnace. It's a cold day here in the Wood household. Back to kinematics here. So now, what is this velocity? This velocity here is, I'm just going to say, calculator memory location A. let's figure out what that velocity is. We can do it. So step one here. I guess I'll work here. Step one says, here's the string velocity. Velocity of that pulse, or a velocity of a disturbance going through a string that's held under tension. Could be a pulse or it could be just a general wave, is T over mass density. So we have the following. We have string tension is 2,200 newtons. That's my numerator. My denominator is the linear mass density, which here it says the mass is 123 grams. So I'm just going to instinctively go to kilograms, because if I'm dealing with newtons, then that implies you got to deal with kilograms, meters, and seconds. So 0.123 kilograms per the length. What's the length of the string? It's 14.7 meters. All of that's given, 14.7 meters. So here's the string velocity, which I'll store in memory location A. What is 2,200 divided by 0.123 divided by 14.7 square root? It's 512 and some change. 512.7 meters per second, which is faster than the speed of sound, which is not at all hard to believe, because compared to air, a string can carry sound very efficiently compared to air. So this is I'm going to put this in memory location A. That's the velocity of this disturbance, in this case, a pulse going through a string. Store alpha A. All right, and then back to kinematics. I have my final velocity is unchanged. You know why? Because there's no x acceleration. Because look at the expression for the velocity. Velocity depends on string tension, which is constant, and the linear mass density of the string, which is constant. So velocity is constant, which means acceleration is 0. Time is question mark. For pulse number 2, which is that blue pulse, all right, pulse number 2 is starting from the right side. So here for pulse number 2, x initial equals 14.7 meters. So for pulse 2, x initial is 14.7 meters. And x final, it's the same. They meet right here. So x final, that's the $sign. And you know what? What is the velocity of pulse 2? It's also A, but it's heading in the negative x direction. So that's negative calculator memory location A. So is that, because there's no acceleration. Now, what do we do for time? It's not, we have to do a little time adjustment, because this problem says you fire off pulse number 1. So pulse number 1 takes off and heads rightward at time equals 0. And then you wait 13 milliseconds and fire off pulse number 2. So how do we represent that? I guess I would say this will be T plus, because I have to wait. I'm waiting 13 milliseconds, 0.013 seconds. Then I guess I'll call this T. This is one way to do it. The alternative is you could call this T, and you could call this T minus 0.013, but I think that's the equivalent. So anyway, I have to deal with the fact that these are not sent at the same instant in time. So that's how I deal with that situation. So there's my kinematics table. So we're back to just generic kinematics. Step number 3. For pulse number 1, I'm going to do this. X final equals x initial plus vx initial times time plus 1/2 a sub x t squared. So that's the old kinematics guess and check. So maybe this will help, maybe not, but let's see. Low hanging fruit. This is my $sign. That's $sign. This is equal to 0. This is equal to 0. So you know what I get? Kinematics for pulse number 1 says the following. X final, which is my dollar sign, equals AT. That's all I can get out of my kinematics for pulse 1. And I'm fine with that because now when I look at pulse 2, I'm going to play the same game for pulse 2. X final equals X initial plus VX initial T plus 1/2 A sub X T squared. Do the same. I'm going to move over here. Here's step 6. So X final, and this X final is the same as this X final. So that's the linkage. Time doesn't link them, but position links them. All right, so X final equals X initial, which is 14.7, plus VX initial, which is negative A times time T plus 0.013. And then that's it. I guess that's it. So for pulse number 2, I have the following. X final equals 14.7 minus capital letter or calculator memory location AT minus memory location A times 0.013. And that equals the X final from pulse 1, which was A times T. All right. So again, let me make sure. This is the result. This is XF for pulse number 1. So this was XF for pulse number 1. And all of this right here is XF for pulse number 2. Unless I made some mistakes. This is all of this is XF for pulse number 2. So let's do this. Let's solve for T. Solve for T, then for XF. Okay, so if I solve for T, look at number 7. I'm going to get 14.7. Did I alpha A this? I did that. All right, so 14.7 minus alpha A times 0.013 divided by 2 divided by alpha A. So I have T. I got my time. They meet. These pulses meet at T equals 0.00783 seconds. And we have to be careful. This is from the perspective from pulse 1's perspective, from pulse 1's perspective, reference frame. Okay, so number 10. So what is XF? XF, I'm just going to recycle this. I'm going to reuse this version. XF equals calculator memory location A times calculator memory location B, because I'm going to put all of this into calculator memory location B. So when I take memory location B, store alpha B times alpha A, I get 4.017. That's where they meet. These pulses meet at 4.017 meters. So the real takeaway from this problem, it's kinematics. I mean, the beauty of this problem is not kinematics. That's not the central focus right now. Right now, kinematics is just another tool that we have mastered and are happy to use. But the new introductions are right here. It's this velocity of a wave or disturbance traveling through a string in tension, and it's this mass density, mu equals mass per length. And just a clever application of those properties. Okay. That's that. So let me do a sanity check on time. It is now almost 4 o'clock. So that will be good. So you know what? You know what I'm going to do? I'm going to flip and then flop. I'm going to flip flop. So I'm going to go, I take that back. I was going to change the home. but we'll be good. You guys will be good with the Sunday homework because we'll accomplish a lot on Wednesday. And this is 6 quizzes. So let's do this. I'll say quizzes 1, 2, 3. There was no quiz 5, huh? Is that right? Quiz 1, 2, 3, 4, 6. So we'll be due. I'm thinking, and you guys can speak up, but quizzes 1, 2, 3, 4, 6 deadline. Midnight tomorrow. I'm thinking midnight tomorrow. 11:59 p.m. on Wednesday, December 8th. Yep.
That works for me.
Okay. That's good. And that will be adjusted if Wiley Plus is permanently broken, then we'll figure it. But my guess is they'll figure it out. But all right, these quizzes, which I'll make sure they have a deadline in Wiley Plus. And again, I don't know what happened to quiz 5. There was probably some reason behind that. 1, 2, anyway, these quizzes covered today, you will need to do them before midnight tomorrow. So, okay.